because I wanted to let you know that phases in chemical reactions, 6.1e, is officially black diamond material. I don't feel like we have time. I don't feel like you're going to get that much out of it. I feel like it will confuse a lot of you. But if you do want to learn it, it's not that bad. Okay. And I can't draw a diamond apparently, so I'm just going to do that and not color it in because it looks better. Okay, so that's 6.1e is black diamond. And we are going to go to page 27. 27. 6.2d. No? What page is it? 27, but it's 6.2c. Okay, there we go. So this is basically the entire 6.2c is on strategies for balancing equations. So you can just do it by trial and error, and that will work some of the time, and that's fine. If you're getting it and you don't need to use any of these strategies, that's fine. But these are things that will make the harder ones easier. Yes? So if you get stuck, you're going to try and remember these strategies. So strategy number 1, we did look at this last day. We wanted to use a little chart. Do you have to use a chart? Are you required to? No, but if it's helpful, you can. So say, for example, we have this one here. And we're starting out, and we look on the left-hand side, we have 2 irons. On the right-hand side, we have 1 iron. We have 3 oxygen on the left, 2 oxygen on the right, 1 carbon on the left, 1 carbon on the right. So one of the things that you'll want to do is you balance lone elements last. What on earth is a lone element? It's an element that is not part of a compound. So who are our lone elements here? Carbon and iron. So we're going to balance those last, which means we should probably start with oxygen. And if you remember from last day, here we have a 3 and we have a 2. If we have a 3 and a 2, we should be aiming for how many? 6. So let's try and get 6 oxygen on the left. What coefficient do we need to get 6 oxygen on the left? We need a 2. And let's make sure we change all our numbers down below. That gave us 6 oxygen, but it also changed the number of iron. How many iron do we have now? We now have 4 iron. All right, and we need to have 6 oxygen on the right. So that means we need a 3. Okay, and so now we have 3 times 2 is 6 oxygen, but that also changed the carbon to 3. But because we have these lone elements, we can just balance them on their own now. Super easy, right? We just go, oh, I need 3 carbon, so let's put a 3 in front of carbon. I need 4 iron, so let's put a 4 in front of iron. Is good? Okay, so little 2 and 3 thing, balance your lone elements last, use a little chart, okay? Now, all these notes in here, this is in case you were away or something, you know, you could follow through if you were just reading it on your own. We're just gonna go through all the strategies. Strategy number 2, even and odd. So that's like the 2 and 3. We just did that where we had the odd and even with the oxygen, So we're not going to go through that. So we're going to keep skipping down to page 29. Strategy 3. Strategy 3 is put the coefficient on the compound first. Okay? This works well if you have a synthesis, if you have a decomposition, or if you have a single replacement. By the way, what type of reaction is this one here? K plus O2 gives K2O. That is synthesis. Two things become one thing. So if we take a look at this reaction, let's balance it by putting the coefficient on the compound first. So what that means is if I have O2 here, so I need to put a 2 here to give me 2 oxygens, but that changes the potassium to 4, which means we now need to have 4 potassium. And everybody's good, 4, 4, 2, 2. Would it actually really matter too much if we did it in a different order? Probably not. Let's try it. Let's say instead of putting that 2 on the K2O, let's say I decided to go with K first, and I have 2 on the right. Let's say I put my 2 on the left. Then I'm like, okay, now I need to balance oxygen. I've got 2 on the left, so I need to put a 2 on the right. It ends up being virtually the same process, except for now I have to change this 2 to a 4. But it's not a big deal. No matter which way you do it, you're getting the right answer. Yeah? Okay, page 30. We're going to skip the exercises. We'll let you work on those later. This is a big one. Deal with atoms in the most complex compound first. The most complex compound. This will be the one with the highest total number of subscripts. That is our most complex compound. Look for the most subscripts, and that will be your most complex compound. This is especially useful if we're doing double replacement and if we're doing neutralization, because neutralization is just a special form of double replacement. So let's look at this reaction that we have here. What type of reaction is this? That is double replacement. We have compound plus compound gives compound plus compound. Out of those 4 substances, who is the most complex? Who has the highest total number of subscripts? Let's look at our subscripts. We have a subscript here, we have a subscript here, we have a subscript here, and we have no subscripts in the last one. Who's the most complex? Who has the most subscripts? Iron sulfide. So this one here is the most complex. In other words, the highest number of subscripts, which means that we're going to balance Fe and S first. Okay, so let's do it. You can balance it other ways, but this will make it go the most smoothly. Okay, trial and error will probably work here. All right. So here's our first step. We want to balance the Fe and the S first. And I've taken the liberty of doing the first little step for us here. We have 2 Fe's on the right. So let's put a 2 in front of FeCl2 on the left to give us 2 Fe's on the left. But remember, that will also change the chlorine. How many chlorine do we have now? 6. So we would need to change that to a 6. Now we have balanced Fe. That looks great. Who will we balance next? The sulfur, the other part of the most complex compound. So let's do sulfur. We have 3 sulfur on the right. So let's make sure we have 3 sulfur on the left. That changed our sulfur to 3, but it also changed our sodium to 3 times 2 is 6. And this is why I like to do the most complex one first, because now when I look at it, I can pick either sodium or chloride. And guess what? It fixes both of them. And if you do it that way, it'll always work that way. It'll be like, oh, I just have to add a number here. Woo, how pretty. Okay, so we can skip ahead. This is just showing all the steps written out. There's the exercises. Here we go. Strategy 5. Here's a weird example where we're practicing putting coefficients on the lone element last. And I don't know what's up with this reaction. I don't know what the heck an NaZN4 is. It makes me unhappy, but we're going to balance it anyway. Okay? Who is our lone element here? Na. Na is our lone element. So we're going to leave it till the very end. At this point, it doesn't really matter whether we do the iodine or the zinc. However, I think because zinc has a bigger number, maybe I'll go with that one. Does that sound good? Sort of going along the more complex route. So we have 4 zinc on the right. So let's get ourselves 4 zinc on the left. That changed our zinc to 4. But it also changed our iodine to 8. Well, I can fix that. I can put an 8 in front of NaI. That changes our iodine to 8. And it changes our sodium to what? Is it 8? Tricky. When you have elements in different compounds, sometimes you forget, and you're like, oh, it's 8, but it's actually 9 because we have 8 in the NaI and 1 over there. So that's going to be a 9. But guess what? We have sodium all by itself, so we can just toss a 9 in front of it, and everybody is happy. And I crossed out 1 and wrote zinc instead of writing 4. Okay, that was clever of me. Zinc, sure. All right. Skipping along. We're now on page 33. Treat polyatomic ions as a single unit as long as they're on both sides. If I had CaCO3 reacting to form CaO plus CO2, I do have a polyatomic ion here. I have CO3. Can I treat it as a group? No, because there's no CO3 anywhere on the other side. So you can only do it when you have CO3 on both sides. So if we look, though, at this equation here, we have a polyatomic ion on both sides. We have NO3 and we have NO3. So we're going to, rather than splitting it up into oxygen and nitrogen, we're going to keep it together. We have 2 NO3s on the left, and there's no brackets and no coefficient. There's none of that on the right-hand side. So we just have one NO3. So let's balance something. Doesn't really matter. We don't have any huge subscripts, so we could pick anything with a subscript. Let's do nitrate because it's here. Okay, let's put a 2 in front of NaNO3. That changes NO3 to a 2. It also changes Na to a 2. So now we need to fix sodium because I have 2 on the right and only 1 on the left. So let's put a 2 in front of NaI. That changes Na to a 2 and it changes I to a 2. And we look, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, like a ballerina. Okay. Let's try this one here. Which polyatomic ions do we have? We have ClO3. Who else do we have? CO3. And we have them both on both sides, so we can treat them as single units. Who should we balance first? Tell your partner, who should we balance first? You want to balance the ions in what? The most complex compound. Who is the most complex compound? The one with the most subscripts. Who has the most subscripts? Yeah, if we go along and we look at our subscripts, we got a subscript here and here, we got it here and here. But when we get over, we got 1, 2, 3 subscripts, which is more than any of the others. Yes? So let's balance the one with the most subscripts first. That would be our Fe and the CO3. So doesn't matter which one you do. Let's start with Fe. We have 2 on the right. So let's put a 2 in front here to give us 2 Fe's. Have we changed anything else? Yes, we've changed the chlorate. Now we have, everyone, how many? 6. Good. We're going to keep working with this compound. We fixed iron. Now we're going to fix carbonate. There are 3 carbonates on the right, so we need to have 3 carbonates on the left. And that changes this to 3, but it also changes the potassium. How many potassium now? Everyone? 6. So 2 matches with 2, 3 matches with 3, and guess what? I got KClO3. If I just put a 6 in front there, both of those become 6, and we're good. Is good? Okay. All right, strategy 6. I think we have a strategy 7 coming up. Yep, strategy 7 is on page 35. This strategy works best with single replacement reactions and with neutralization reactions. If you have water, it can often be very helpful to not actually write it as water, but to rewrite it as HOH. Okay, so we're going to do that. We're going to take water and we're going to rewrite it as H and OH. And we're not going to balance hydrogen and oxygen. We're going to balance hydrogen and hydroxide. It will make balancing way easier. If you leave it as water, the hydrogens and oxygens get a little tangled. Okay, but if you separate out hydrogen and hydroxide, it becomes much nicer. So over here on the right, we've got hydrogen and we have hydroxide. Okay, and the only thing that's unbalanced right now is the hydrogen. So we can put a 2 here, which gives us 2 hydrogen, and it also gives us 2 hydroxides. So now I need 2 hydroxides on the right. Just put a 2 in front of the lithium hydroxide. That gives us 2 of those. That will also give us 2 lithiums. And now I have a lone element lithium that I can just throw a 2 in front of, and we're all done. Did that seem pretty straightforward? It can be less straightforward if you leave it as H2O. If you want to try it for yourself sometime, just give it a go. I'm not going to bother because I like doing it this way. It makes me happy. All right, page 36. What type of reaction do we have here at the top of page 36? What type of reaction? See if you can recognize it. We have neutralization because we have H, which tells us that we have an acid. We have OH, which tells us we have a base. You have to have both of them for it to be neutralization. Some reactions can have a base but no acid, not neutralization. You might have an acid but no base, not neutralization. You have to have both. Okay, and we have H2O, and guess what? We've got H's and we've got OH's and we have a water. So let's split that water apart, kind of, into the H and the OH. So we're going to rewrite water as HOH. Okay, and we have our hydrogen. I like highlighting them. You don't have to. By the way, do you have to draw this little table underneath? No. If you're finding that if you get to a question and you're getting stuck, that might be the time where it's like, okay, I'm going to try the little table and see if it helps me. But feel no obligation to do the little table. All right. Which compound should we be focused on balancing first? Who should we balance first? I only heard it from my front row. In fact, not all my front row, just these 2 ladies in front of me here. So you guys get to be quiet now, and the rest of you are gonna tell me which compound. I'm just gonna label them A, B, C, D, and actually we're gonna vote. Okay, A looks like this. Fingers flat, thumb on the side. That's an A. B, fingers point up, thumb on your palm. That's a B. C looks like this. And then D, pointer finger goes up, and you make a circle with the rest of your fingers. Pointer finger up, circle with the rest of your fingers. So you get to vote A, B, C, or D. Which one do you like? D, yes, because it is the most complex. It's got subscripts everywhere. All right, so we're going to be balancing the iron ion, and we're going to be balancing the carbonate ion. Doesn't matter which one we start with. Iron comes first in the compound, so let's do that first. We have 2 iron, so let's put a 2 in front here. That changes both the iron and the who. It changes iron and everybody? It changes the iron and the OH. Yes. How many OHs now? 6. Excellent. All right. Let's now do, who should we do next? We did iron. CO3. How many CO3s on the right? 9. That's right. There are 9 CO3s on the right. Are there 9 CO3s on the right? There's 3 CO3s on the right. Okay. 3 CO3s. So we need to have a 3 here. Okay, that's going to change CO3 to 3. And that also changes hydrogen. So now instead of having 2 hydrogen, we have 6 hydrogen. And guess what? If I look at hydrogen or I look at hydroxide, I need to put a 6 here to get 6 hydrogen. I also put a 6 there to get 6 hydroxide. 6, 3, 2, 6. Everybody matches. Yay! Okay, isn't that lovely? Okay, so between those little tips, balance your lone elements last, most complex compound first, and change your water to HOH. That'll be really, really helpful, I think. Okay, so when you go, you're going to actually start on page 28. And I would say you don't necessarily have to do every question. Maybe do every odd question. Or if you're like, you know what, I really want to nail this test and I want to practice them all, go for it, do it. But the one thing that you're doing here in addition to balancing is you're also writing down what the reaction type is. And you don't have to write out the full word. You can write syn for synthesis, dec for decomposition, SR for single replacement, DR for double replacement, nu for neutralization, and com for combustion. If you want to write out the whole thing, you can. You don't have to. For single replacement, you can also specify single replacement metal, single replacement non-metal. I can't remember what I did in the answer key. I can't remember whether I went both or just put them both together. So whatever you like. Okay. Oh, I forgot one thing. Where was it? It wasn't here. It was the next one. That's okay. I'll find it later. Oh no, it was the lithium one. Ish. Where are you? Not 33. Not 34. Oh, here. Page 35. Page 35. What type of reaction is this? It is a single replacement, and I know it says single replacement metal, and I know you can read, but let's figure out how we know that and why this one is a little bit unusual, okay? It's a little bit unusual because normally in single replacement metal, a metal replaces a metal. I only see one metal in there, yes? However, if we look at what we have, we've got Li, and we're adding HOH. Now this H here, we have OH minus. What does that make this H? That makes that H an H plus, yes? H plus. So that's our cation. What do metals form? Anions or cations? Metals. Do they gain electrons or do they lose electrons? Okay, you need to talk amongst yourselves about this. Remind yourselves, go back in time. Do metals gain or lose electrons? They lose because they've got, like, if you're in column number 1, how many valence electrons? 1, so they're going to lose that 1 electron. So metals form cations because they lose electrons. So even though hydrogen is a non-metal, what's it actually acting like here? It's acting like a metal in that it is the cation. But this is one of the reasons why once we get past that initial, like, figuring out that the non-metal replaces the non-metal and the metal replaces the metal, when you're classifying, you can just classify it as single replacement because it really makes more sense to say it that way, okay? So we have the metal replacing the metal and the hydrogen gets kicked out. Okie dokie? So pages 28 to 30.